All right, our next topic is the normal distribution. We've talked about histograms and how a data set can be distributed, and we've talked about the shapes that they can take if they're symmetric and unimodal or bimodal or skewed. So today we're talking about a specific shape of distribution that's very important in studying statistics called the normal distribution. So let's start with what is normal. What do we mean by normal? Well, let me point out here that this is also commonly called the bell curve. So if you've heard that phrase before, or grading on a curve, the bell curve, the normal distribution, they're the same thing. So what we mean by either of those terms, normal distribution or bell curve, is that most of the data is clustered near the mean value. So it is a unimodal distribution. The data is spread evenly about the mean value, so it's symmetric. Large deviations are increasingly rare, so it sort of fades away to either side, right? So you peak in the middle and then it gets smaller and smaller as you go away. And then individual data result from many different factors. So what causes a normal distribution is any quantity that comes about by many different things that could influence it. Now, not every normal distribution looks exactly the same, but they have these same features. An important parameter of the normal distribution is the standard deviation. And so we'll start to think about this at the end of this lecture in terms of what its standard deviation. For now, larger standard deviation means a wider and shorter distribution. Smaller standard deviation means taller and narrower. All right, so we have two different distributions here. One, which has the normal shape, unimodal, symmetric, fades away to both sides, and one that is skewed. This one is skewed to the right. Remember, the skew is the direction where the tail goes. So what is this one representing? This one is representing the chest circumference of Scottish militiamen, which was a sort of famous old study, one of the early studies of the normal distribution. And that's why this one is that's what's plotted here. But it turns out like all sorts of characteristics of the human body follow normal distributions because there are a lot of factors that go into determining how tall you are, or what you weigh, or your head circumference, or the distance between the tips of your fingers and your elbow. All of those features, characteristics of the human body, tend to follow the normal distribution. There's some average value in the middle, and it's less common to get values that are farther away from that central peak. But not all distributions are going to be normally distributed. On the right-hand side, we have something that's very clearly not a normal distribution. And that comes about either because it's caused by a very small number of factors that tends to push the distribution to have a certain shape, or there could be a boundary that is favored. Okay, and so that's what I would say in this case here. We're talking about population density of the 50 states. And I put favored in quotes because there's lots of different contexts, but the main idea is that the data tends to be pooling around one end of a spectrum. So this is measuring population density. You can't have less than 0. But living in a place that has low population density can be kind of nice, right? You have lots of land available, you have space, right? And so that's a favored end of the spectrum. Lots of states are going to have that value, or have a value in that range. But when that's the case, when quantities are favoring one end of a spectrum, there's really not room for a normal distribution to be there. You can't really have the other side because you can't have negative population density. All right. Another example that I could bring up is like a test, an exam, right? And exams could be really hard, or they could be really easy, or they could be somewhere in the middle. Let's take an exam that was really, really easy. Well, and let's imagine that this scale went from 0 to 100%, right? A really, really easy exam, everybody's going to do great. You're not going to have any values down here. The end that's favored is the 100 end, right? And so the distribution would be something like this. It would be skewed to the left with the peak, in the 90s, something like that. As the exam gets harder, the peak is going to move to the left, and eventually it might look like a normal distribution when the peak is sort of far from those ends of the spectrum. And then if you make the exam so hard that like no one can get anything right, then it would be a skewed right, and you'd have the peak over here. So the context can determine whether or not that you would expect there to be a normal distribution. All right, so I said we were going to talk about standard deviation, and that was going to be an important factor. The picture here might look a little bit familiar, either because you've seen it before or you recognize it from the Moodle page. So I chose this to be the representative picture for our unit on statistics because it's such an important diagram. Now the curve is the normal distribution, and these lines are representing ranges of standard deviation. So let me go back to the slide. So this is a rule that would be helpful to just memorize. Remember this rule. It's called the 68, 95, 99.7 rule. And what it means is that if you have a normal distribution, so that it has to be a normal distribution for this to be true. If you have a normal distribution, 68% of the data is expected to fall within one standard deviation of the mean value. So if the mean value is here and the standard deviation is this big, 68% of the data would either be one standard deviation above or one standard deviation below. So from this dotted line to this dotted line, 68% will fall in that range. If you go out 2 standard deviations to either side, then that accounts for 95% of the data. And 3 standard deviations, you're almost to everything, 99.7%. So this is both revealing something about the normal distribution, but also telling us something about what the standard deviation represents. And what it's representing is really how wide, how spread out the distribution is. Okay, so we can do more with this, and we can create something called a standard score or a z-score. Okay, so standard score and z-score mean the exact same thing. It's usually given the variable z, and the formula is so a z-score applies to any data point in a data set. So any data point in a data set can have a z-score. And you calculate it by taking the data point, subtracting the mean value, and then you divide by the standard deviation. The way I think about it is it's like counting in standard deviations. So let's take an example. Imagine that you got 100. You got a perfect score on an exam, and the average was a 25. And the standard deviation, let me make the numbers easier. Sorry, let's say the average was an 80 and the standard deviation was 10. So the average is 80, the standard deviation is 10. And you got a 100. So 100 minus 80 is 20, divided by 10 gives you 2. And so you would have a z-score of 2. And what that means is you are 2 standard deviations above the mean. So we're sort of using standard deviation like a unit of measurement. You're this many standard deviations above or this many standard deviations below. Now, not all normal distributions have the same exact shape. Some are tall and skinny, some are short and wide, but they do have this common mathematical formula that describes them. And the z-score means the same thing regardless of whether the normal distribution is tall and skinny or short and wide. So a z-score of 2 always means the same thing. You're 2 standard deviations above the mean value. So because this has this sort of universal meaning, we can use it to represent the percentile, or the value, the percent value, where all of the data is less, the percentage of data that is less than that particular value, less than or equal to that value. Okay, so the last thing on here is a big table, but let me just recap this formula. So every data point can have a z-score or a standard score. You calculate it by taking the data point, subtracting the mean, dividing that result by the standard deviation. Then you can take that z-score and look up in a table the percentile, which represents the percentage of data that is below that value. All right, and so this is what the table looks like. Obviously, you don't need to remember anything from this table. If there are problems that we do using normal distributions, I would give you access to the table in order to look up the result. You just need to know how to use it. And there's a few different ways that you could be asked to use a table like this. Now, the most straightforward way is you calculate a z-score and you look up the percentile. So I just said the percentile was 2 a minute ago, I think the example we did. If you got 100 on an exam, the average was an 80, the standard deviation was 10, then your z-score would be 2. So we find 2 in the table. So we have z-scores percentile, z-scores percentile, z-score percentile, z-score percentile. So z-score of 2 corresponds to a 97.72 percentile. That means that 97.72% of all the data is below that z-score. All right, so that's one way that you might be asked to use this table, is find the percentile. But you might be asked the question in a different way. You might be asked what percent of values are above this z-score, or what percent of data is above this particular value. And then you calculate the z-score, you come to the table, but you can't just use the percentile here. This is the percent below. If you want the percent above, what you have to do is subtract this number from 100. Okay, so the percent above a z-score of 2 is, what's that? 100 minus 97.72 would be 2.28. Okay, so 2.28% of the data is above a z-score of 2. And then the last way you might be asked is to say what percent of data is between this value and this value. Okay, so you have 2 particular values, and you say, well, how much data is in between them? What percent of the data is in between them? And that, what you'll need to do for that is look at both of the percentiles and subtract one from the other. So remember the 68, 95, 99.7 rule. Well, let's look at the 68 part. Where does that come from? That's accounting for 1 standard deviation to either side. Well, the z-score counts by standard deviation. So 1 z-score below would be a -1. 1 z-score above would be a 1. So we're looking at the data, how much data would fall between here and here. Well, this says 84.13% is below a 1, and 15.87% is below a -1. So how much is in between? Well, you take the bigger number, you subtract the smaller number, and you get about 68%. Okay, so that's where those rules come from, and you could check the same thing for the 2 standard deviation rule and the 3 standard deviation rule. Now this is all useful information in statistics. It's sort of essential. All of the kind of advanced theory of statistics are built on an understanding of the normal distribution. And so we'll look at some examples where we have normally distributed data and use the z-scores to think about percentiles and assess what it's telling us about the data set, how things are distributed. And so there will be an example worksheet with a video, and hopefully what I'm hoping to do is take the data that I collected from the class about screen time and use that as our starting point. I don't actually know if that data will be normally distributed, but we'll take a look at it and see what it looks like and evaluate whether or not the normal distribution is a good fit. And so I'll put a video up on that sort of as a lead-in to the example worksheet for this week.